We're still discussing about sound wave, and today we will learn about sound intensity and sound intensity level. In a quiet forest, you can sometimes hear a single leaf fall to the ground. After settling into bed, you may hear your blood pulsing through your ears. But when a passing motorist has his stereo turned up, you cannot even hear what the person next to you in your car is saying. We are all very familiar with the loudness of sounds and aware that they are related to how energetically the source is vibrating. The relevant physical quantity is sound intensity, a concept that is valid for all sounds whether or not they are in the audible range. Intensity is defined to be the power per unit area carried by a wave. Power is the rate at which energy is transferred by the wave. In equation form, intensity I is equal to P over A. P is the power, its SI unit is watt, A is area of a sphere in meter squared, and area of a sphere is equal to 4 pi r squared, while r is the distance from the source of the sound in the unit of meter. So the SI unit for intensity is watt per meter squared. And intensity of sound, we can see here, is inversely proportional to area. So because area is 4 pi r squared, then intensity of sound is inversely proportional to the square of distance from the source of the sound. Or we can say that I2 over I1 is equal to R1 squared over R2 squared. And the intensity of sound wave is related to its amplitude squared by the following relationship. I equals 2 pi squared rho v f squared a squared. A here is the amplitude, not the area. This f is frequency. So intensity of sound, it is related also to the frequency squared and amplitude squared. In this diagram, I have a source power P, and the intensity at surface of sphere will be P over 4 pi r squared. That is the intensity. And if we want to see the intensity at 2r, twice the distance, then the energy twice as far from the source here is spread over 4 times the area. You can see there. So the intensity will be 1/4 of the intensity before. And if we make it 3 times, the distance, we make the distance 3 times, then the area covered will be 9 times. That's why the intensity will be spread over 9 times the area. That's why the intensity will be 1 over 9 before. This is called the inverse square law. Sound intensity levels are quoted in decibels much more often than sound intensities in watts per meter squared. Decibels are the unit of choice in the scientific literature as well as in the popular media. The reasons for this choice of units are related to how we perceive sounds. How our ears perceive sound can be more accurately described by the logarithm of the intensity rather than directly to the intensity. The sound intensity level, beta in decibels of a sound having an intensity I in watts per meter squared, is defined to be 10 times log I over I naught. It is in decibels, or it is equal to log I over I naught in bell. You have to know that 1 bell, this is taken from the name Alexander Graham Bell, is equal to 10 decibel, because deci is a prefix, so 1 bell is 10 decibels. This I naught, I0, is equal to 10 to the power of minus 12 watt per meter squared. It is, we call this the reference intensity. It is the lowest or the threshold intensity of sound a person with normal hearing can perceive. I will give you some examples. The threshold of human hearing, the intensity of sound is 10 to the power of minus 12 watt per meter squared. So beta will be 10 times the log of I over I0. It is equal to 10 times log 10 to the power of minus 12 divided by I0 is always 10 to the power of minus 12 watt per meter squared. So beta will be 10 times the log of 1. The log of 1 will be 0. So the threshold of human hearing will be 0 decibels. Another example. For a normal conversation, the intensity of sound is 10 to the power of minus 6 watt per meter squared. So when we want to state this in decibel, then use the equation beta equals 10 times the log of the intensity is 10 to the power of minus 6 over 10 to the minus 12. So it will be equal to 10 multiplied by the log of 10 to the power of 6. It is equal to 60 decibels. And the threshold of pain, the intensity is 1 watt per meter squared. And if you want to state it in decibel, then it will be 10 times the log of 1 over 10 to the power of minus 12. It is equal to 10 times the log of 10 to the 12. It is equal to 120 decibels. In this table, you can see some sound sources example with distance. The one that I discussed, the threshold of human hearing, was this one, the threshold of hearing. It is 0 decibel. The conversational speech at 1 meter, it is about 60 decibels. And then if you have a disco 1 meter from the speaker, it will be 100 decibels. And this is the threshold of pain, 130, or discomfort threshold, 120 decibels. And for a jet aircraft 50 meters away, you will hear 140 decibels. Those are the examples of sound sources examples. Quiet library will be only 40 decibels and so on. Sound intensity level is not the same as intensity. So here we can see that the intensity level in decibel is comparison of the sound energy of a noise with that of one just detectable at the threshold of hearing. But we state it in logarithm. While intensity, it is absolute measurement of the sound energy incident on an area in a given time, and the unit is watt per meter squared. Yeah, you have to be able to make a difference between intensity level and intensity. Let us assume that there is a sound source and an observer at a certain distance, and he can hear the intensity level of beta decibels. Now, there are n identical sound sources, and the observer at the same distance can hear the intensity level of beta n decibels. The sound intensity level of n identical sources, each of sound intensity level beta, can be derived as follows. This beta heard by the observer is 10 times the log of I over I naught. And beta n will be 10 times the log of n times I over I naught. Remember that we can only multiply the intensity by the number of sound sources, not the intensity level. So when there are n sound sources, the sound intensity will be n times, not the sound intensity level. We can only multiply the intensity. And if I subtract beta n minus beta, it will be 10 times the log of ni over I naught minus 10 times the log of I over I naught. And for logarithm, a times the log of b minus a times the log of c will be equal to a times the log of b over c. So it will be equal to 10 times the log of ni over I naught divided by I over I naught. So beta n minus beta will be 10 times the log of n. So beta n will be equal to beta plus 10 times the log of n. So this is the equation of the sound intensity level of n identical sources, each of sound intensity level beta. An example for this is page 178, number 8. In a child clinic, a baby is crying at sound intensity level of 80 decibels. Assume 10 babies are crying together, each with the same intensity level. What is the intensity level produced? So we know that beta is 80 decibels and there are 10 identical sound sources sounded together. So beta n equals beta plus 10 times log n. So it will be equal to 80 decibels plus 10 times the log of 10. So it is equal to 80 plus 10, it is equal to 90 decibels. So you can see when a baby is crying at 80 decibels, 10 babies are crying together with the intensity of 90 decibels, not 800 decibels. Yeah, you have to pay attention to that. Now we assume that there is a sound source and an observer perceives the sound intensity level at distance r1 as beta 1. When the observer moves to a distance r2, he perceives the sound intensity level to be beta 2. I will derive how we can relate beta 1 and beta 2. Beta 1 is equal to 10 times the log of I1 over I0. Beta 2 is 10 times the log of I2 over I0. Beta 2 minus beta 1 is equal to 10 times the log of I2 over I0 minus 10 times the log of I1 over I0. And we know that a log b minus a log c is equal to a log b over c. So it is equal to 10 times the log of I2 over I0 divided by I1 over I0. So it is equal to 10 times the log of I2 over I1. And we know that I1 over I2 is R2 over R1 squared. That is the inverse square law. So I2 over I1 can be substituted by R1 over R2 squared. And that's how we get 20 times the log of R1 over R2. That is beta 2 minus beta 1. So beta 2 is equal to beta 1 plus 20 log R1 over R2, or we can write it down as beta 1 minus 20 log R2 over R1. Yeah. So this is the relation between beta 1 and beta 2. And for an example, I will take it from page 178, number 10. At a distance of 2 meters from the detonation place, the sound intensity level is 90 decibels. What is the sound intensity level at a distance of 20 meters from the detonation? R1 is 2 meters, beta 1 is 90 decibels, and R2 is 20 meters. So we want to find beta 2. Beta 2 equals beta 1 minus 20 times the log of R2 over R1. Beta 1 is 90 decibels, R2 is 20, R1 is 2. So this is 20 times the log of 10. It is equal to 20. So 90 minus 20 is equal to 70 decibels. So of course, when it is further away from the detonation place, the sound intensity level heard will be smaller than 90 decibels. To generalize the two equations, we can combine the two equations before. The sound intensity level perceived when there is a change in distance, and also the amount of sound source can be written down as this. So this is the combination between the two formulas that we discussed. Beta 2 equals beta 1 minus 20 times the log of R2 over R1 when there is a change of distance, plus 10 times the log of N2 over N1 when there is the change in amount of sound source. Yeah, so the example will be taken from page 176, number 3. The sound intensity level at a distance R, R1 is R, produced by a sound source is 50 decibels. Beta 1 is 50 decibels. Calculate the sound intensity level of 10 identical sound. So N2 is 10, N1 is 1. Identical sound sources at a distance 10R. So R2 is equal to 10R. We will use directly this equation. Beta 2 equals beta 1 minus 20 times the log of R2 over R1 plus 10 times the log of N2 over N1. Beta 1 is 50, R2 is 10R, R1 is R, N2 is 10, and N1 is 1. So it is equal to 50 minus 20 times the log of 10, it is 20. 10 times the log of 10 is also is 10. So it will be equal to 30 plus 10 equals 40 decibels. I will discuss for you the example problem on page 176. Number 1, a sound source of power 50 watts produces sound wave that is transmitted throughout the surrounding. Calculate the intensity of the sound wave at a distance of 10 meters from the source. We have the equation of I equals P over A, so we want to find the area first. The area will be the area of a sphere. 4 pi r squared, it is equal to 4 pi times 100 in meter squared. So I equals P over A. The power is 50 watts divided by 400 pi meter squared. So it will be equal to 1 over 8 pi watt per meter squared. Number 2, a firecracker is detonated at a certain place. At a distance of 2 meters from the source, the sound intensity is 10 to the minus 4 watt per meter squared. Calculate the power of the detonation and the sound intensity at a distance R2 of 20 meters from the place of detonation. Yeah, we will find the power first. The power is I multiplied by A. Yeah, I intensity multiplied by area. It is 10 to the minus 4 multiplied by 4 pi r squared. So it is equal to 16 times 10 to the minus 4 pi in the unit of watt. And R2 is 20 meters, so we can use this inverse square law. I1 over R2 equals R2 over R1 squared. I1 is 10 to the minus 4 over I2. This is what we are going to calculate. R2 is 20 meters, and R1 is 2 meters. So from this equation, you can find that I2 is equal to 10 to the minus 6 watt per meter squared. So now, please do yourself as an exercise the example problems in your book, page 176. This is what I have discussed. And do the more problems in your book, page 178, number 8 and 10. These have also been discussed. And now try page 180, number 16, 19, and 20. You don't have to submit it, but please do this by yourself because this is going to be your exercise. And if you have any questions, you can ask. Thank you. I hope this video is useful.